At IU, I had once an introductory course. They offered it before this course, one afternoon by, I can't tell you the name, just a moment. The name.
Today might be that quiet day. I'm also thinking of skipping the meetings this week because there's not much, very good. I see, because if I don't have power, I don't have the ability to meet with people. That's
Robert King. No, Raymond Shepard, he was giving a presentation.
Raymond, what?
Shepard, this guy gave us an introductory at the URATS.
I don't know him.
I think so. So he was giving a whole lecture about quantum computing here at IU one afternoon. And that was the first time I really understood a little bit. And now I come to the class, but this was just this spring. This spring was the
Raymond Shepard.
Yeah.
And the question is, why did he do it?
Because they offered it from UETS, and I was in France at that time, and it was in the afternoon, and I just said, but I have signed in for this class, or I was in the process that they allowed me to go here, and I said, okay, I want to catch a first idea what it's all about, and it was an afternoon, and it was very. So he's around here. I don't know which the physics department.
Does that sound like a really good introduction? I mean, the way it looked, yeah.
Yeah, it was good. It was very good. He talked a lot. Yeah, it was. It gave me a first idea of what was all about. Not that deep, right? No misty state.
Well, misty state is actually simpler, but yeah, you can calculate it without having to use the matrices, and you kind of trace the thing as if you were doing counting bits in classical computing.
I mean, one is the shortest box fair, and he said that you can calculate everything that is in the box fair, but at the moment you resolve it, it collapses. You have one solution, right? So that was things that he explained, and then they showed us QuizKit, and he showed another software that was graphical to open source that you just could drag and drop.
That's right.
And these were the two softwares they showed us. And it was very good to get the first idea what it's all about and where you would have to dig in when you want to learn more. But, yeah.
All right. It's 8:47. We need to get started. We have 4 people online, 2 of which is me. And then we have Ahmad and Blake. Maybe first we want to verify that the people online can hear me. So can you write your first name backwards, please? I'll start. Oh, but where it's that's very good. And that's me. Very good. All right, so I said the first name, so I think maybe I might wrote the second name, last name, but I'm not entirely sure how to count them. So anyway, this looks good. People hear me, and now we're gonna get started. I'm recording. I'm on the desktop. Today is Thursday. I got the iPad with me, and we have at this point done some things. I'm going to close the chat and the participants, and if anybody needs anything, you can speak up, or you can write in the chat, and I will be notified. I'm going to also close the controls, although now I'm changing my mind, and I'm going to close the video. So I only have audio and the screen, which I'm sharing. And so we're now trying to wrap up the second week. We have Thursday today and Friday tomorrow. As indicated earlier, I'm going to close this down. As indicated earlier, you have 2 deliverables for this week. And again, it's flexible. Whenever you feel like it, do it. And if you need help, you should ask for help as it's available. We have some problems, though, that in the sense that I wanted to meet with you every day, not every week. And this is what we have done so far. So people that I haven't met with are basically here at the bottom. And then I had to reschedule, but I have not met yet with Danielle and also Shivam. Shivam, I think, had some issue and had to go to the doctor. And so skipped his appointment, but apparently he said he's okay, so I don't have any details about him. But I think I met with everybody. Mostly, okay, so then this week, what exactly do we do this week? And my problem this week is that if you look into the office hours, I indicated here that there was a storm on Tuesday. I don't have power. I mean, Elmont has power. But I don't. I don't, so I wasn't available yesterday, though I came into office here. And I have this listed over here, though I doubt I can sustain it. So now I'm thinking that I should stay in touch. I'll come in the office here for as long as I don't have power at home. I'll come in the evening, catch up with email and stuff like that. I haven't checked email since last night. And if necessary, I can Zoom from here. But I really hope that they will reestablish services soon. And in that case, we can resume meetings. If we so we have a storm like this exactly at about this time every year. And it depends when it hits and what trees are falling down. So then my thinking was, after a very successful first set of meetings that lasted since from Friday to it was supposed to be until yesterday, so a long range. I thought maybe we can skip the second week meeting and then just meet on the third week with the information and the materials from week 2 and week number 3. I go under what's new as far as the way that I post the link over here, and apparently it was saying that the county declared disaster, but I'm not sure where that is written anymore. It's the county. The county at the time says this is actually a problem. And we're done with the weather. The weather is okay right now. There's just a lot of debris everywhere. Now, I'm going to say that this week we have 2 deliverables. One is the diagnostic quiz that we talked about. And then the second thing was the bursting Vazirani. We did go through bursting Vazirani. I posted all the videos yesterday, the one that I owed you from Tuesday and then the one from Wednesday. And I'll show you where they are. So if you click on the 25th, this is the part that I didn't post at the time, but I did post yesterday. And you remember that the way we worked this out was that I'm going to come here and I say, I worked out something at the time that wasn't good because I forgot to apply the control knot. And so, you know, at the end I said, oh my God, I messed up. What do I do? I'll show you what's in little cubits over here, and then we'll come back on Wednesday. We did come back on Wednesday, and the video from Wednesday is on the 26th. If you click on it, you get the derivation that we worked out, which I hope I can just give you as a snapshot here somewhere. This is some question that we had at the end. This, I suppose, is a derivation, might be in the process of being derived. So at this point, do you need anything?
Yes, do you have a pen?
I have a pen that was
That's
on the,
great.
it was on the thing. And so we worked out the derivation for the base kickback, which says that if you put a plus and a minus in the inputs, with the plus going on the control and the minus on the target, what changes is the control, not the target. Great. I also wanted to clarify that a while ago, when I still had power, I took some pictures from the book and I wrote them here. Mainly my original motivation was to actually show you how the CNOT works. But then I thought, hey, all these pictures from the first 30 pages of Q's for Quantum are things that you should know now by heart. I mean, just understand it very well. And as I scroll through this, there's this part at the end. There is a nice example of how to calculate, but nobody knows where this is coming from. He just says, take this state, put it into it's a state of 2 qubits, right? So it's a superposition of 4 possible states. Each one has 2 qubits. So if you feed that into a circuit with 2 gates, a NOT and the PEAT, both of them 1 qubit gates, what happens what comes out of that? And what happens is this one. But guess what? This one is an entangled state. And so we need to bring up that topic. And I guess for 27, I have nothing. And for 28, I have nothing. And I have to wrap them up accordingly. Last night when I came here, I did something that I'm going to show you in a second. As far as the little qubits is concerned, just looking at the table of contents, we say we understand superposition. It has to do with one qubit that may have more than one outcome. We understand what happens when we have more than one qubit, but really we only use two qubits, and that's a string that has first and second, first and second. Phase is a minus, and we introduce some rules. But for one qubit transformations, we have one qubit gates. If we have two qubits, we can use gates with two inputs. And we are basically where we have to discuss entanglement. You cannot discuss entanglement if you're focusing on just one qubit. But as I said, we are now processing two qubits. The truth is that we only have one gate that we talked about that is a two qubit gate. That's the control node. And we have all the other gates, well, not many, H, X, and Z, and they are supposed to help us with whatever, but they are one qubit gates. We can talk about swap, and I briefly mentioned it. We can talk about control Z. And soon at some point, control Hanuman is going to play a really important role for us. But seriously, all we have at this point is X, C, H, and C naught. And if you click on entanglement, my main goal today at some point will be to ask you, can you use unistic state formalism and tell me what's happening in this circuit? But that's not really a goal for this week. As I'm looking again at this one, we have phase kickback and we have Bernstein-Vazirani. I did show you at some point under what's new that there is a video, this video, which I'm not going to play anymore, but this is Abe, and you've seen this video. And he actually explains how to do things. But the new interesting thing is that all the code that he types, I have, but it doesn't work anymore. And now I get another unbelievable, these guys. Hang on, let me just quickly take this. They're not supposed to call me now. Hello? Yes, this is me. I don't right now. If you give me a phone number, I'll call you back around 10:30. I'm in the middle of a lecture right now. Like and then 765 349 6793, and then who do I ask for? June with Katie, and so this is 765-349-6793. Yeah. Good. I'll be able to call about after 10:30. But thank you so much. Bye bye. Thank you. And so I'm going to tell you that if you were to follow this, where else do you find it? Well, guess what? You can find it here. We need to define the problem, which I think I defined yesterday, and then we also need to implement it. And when I implement it, this is my advice for you, and that's what worked as early, I think, as March, but things have changed, so this doesn't work anymore. Some things are not working. For example, the backend simulator. Okay, so the good news is that I came here last night and I modified it so it works, and I'm going to go on the students and I'm going to click on GRU, and GRU has a week 1, and now we're doing week 2, and this is the thing that we're going to do today. Bernstein-Vazirani, the implementation goes like this. Here's a secret number. I changed it. The program says, I don't care what secret number you give me. If you give me a list of indices that matches those and the 1011, whatever, then I'm going to build a circuit for you. And then I'm going to do other things for you to be sure that it's working well. So as you remember, when we started, I have in the chat something. Hello, Carla, hello. Okay, so hello back, but is there anything that you need that I should help you with, or it was just a hello because you just came? can you just say something so we can be sure that you can say and we could hear you? Just say if you can. So as I said, if somebody writes something in the chat, I get notified, though sometimes I answer a little bit late. So this was a 3-minute delay, but I get to it. So it is not clear to me if Carla said hello just because she had joined, or maybe she said hello because she needed something. So maybe she doesn't need anything. If you don't need anything, that's okay. I think she said hello because you said hello on the phone. Oh, I see. That's possible. Oh, and then let me write down who's here, right? I guess, so, so if any, don't anything, Brad, that's very good. So I'm going to say that Elmar is here, and so am I. And then online, very briefly, just to get an idea of who and what, I'm online, and so am I. Twice with and then I had Ahmad F. And then Alisa, I just joined, and that's good. And then we have Carla Blake. Just acknowledging people who are here, Jack, and that's who is online right now here. So if anybody has any questions, write them in the chat. I might just be 3 or 4 minutes late to notice that. But if you were to stop me and say, hey, I have a question, just out, with the voice, then that would be perfect. So I'm going to close all of these now, and I'm glad for everybody being here. So I think you remember from week number 1 when we established environment, that to solve the probability problem, we had 2 options. One is to simulate and then hope that the simulation is reliable, it matches what we're discussing. And when we run it, if the numbers are big, by the law, big numbers are frequencies are going to converge to something that we can claim to be probability. And second thing is that I want to be a mathematician and I need some backup. I will think about counting the cases that I'm interested in and then divide by total number of cases. But what if I count something twice? What if I skip something in my counting? So the second option, other than the simulation, was to actually use the program to count. So today, I am going to show you that you could also simulate with Qiskit and get some distribution. For Gaussian running, it doesn't make any sense to simulate because, as I said, you will be able to get the number, a secret number in 1 try. But if you simulate, then you can run it and it gives you like 1,024 shots. And then the result, I put shots to be 1 somewhere in here. I'm not sure where. Okay, shots is 1 here, right? If I take this out, it's just going to run it 1,000 times or 2 to the 10. So then you get to see a probability distribution of your outcome. In this case, because it's always that number, this is proof that it finds it in 1 attempt. But then if I were to just run it as a simulation, every single time we'll find it because it can find it in 1 step and then it's always the same. That's not the same when we do an entangled state, because the entangled state would be a superposition of 2 outcomes, each one a 2-qubit outcome, and you don't know which one you're going to get because the probability of getting one or the other is 50%, kind of like measuring Hadamard gate output, except that's a qubit, 1 qubit. And if you measure, then you will see I get either this or that, but there is a distribution and there's an ideal distribution and there's another one that's like simulation. Now, this is what we have done up to this point. We just say back to being a mathematician, maybe I want to count. I don't count here. I'm just calculating the actual expression. And then the question is this expression the one we expected? And I mentioned this to you before that you should accept these challenges, which, by the way, I'm going to try to solve tomorrow as a wrap up for the whole week. Could you label these states? And the answer is absolutely. One is the black circle and white is 0. And then you can look at them and calculate the probabilities out of the formula that I gave you, n squared over m plus m squared plus n squared, or n squared over n squared plus m squared. And then you write the actual conventional expression by taking the square root of that and then using those as a probability amplitudes. And then the last challenge that I gave you is, okay, if we also use the z-gate, how is the z-gate going to make transitions between these states, or does it need more states? Okay, so that's a good exercise, but it's not priority for us right now. So now I'm going to say that given that what I explained, I would like to work on the stop sharing this one, and then I'm gonna go on the iPad, and I'm gonna start sharing say, okay, this is my note, I mean the pencil. And now I want to share the content, I'm gonna share the screen, I start broadcasting, and then I go into my freeform thing. Come on, freeform. And this is the thing that we did yesterday, so I'm going to go to the eraser, and I'm gonna erase this part. Okay, so what I would like to do, remember, which we proved twice, one in the little cubicell in a certain way, and then we proved it by carrying around a superposition here, like this superposition which I'm erasing right now. Can't, but it should, doesn't want to move now. The eraser is stuck. Come on, eraser. Okay, then eraser now catches up with me. So this is a superposition, and I erase it. So now I'm going to define the problem. I'm going to define two problems, one of which classically is going to be very easy to solve. And then I'm going to say the other one is not possible to solve classically quickly. Okay, eraser, you're getting stuck. I don't like you, eraser. I mean, I do, but not that much. It's just like 6 out of 10. If you want to know eraser, and you can shape up better. So there's a green, which now becomes white, and this is the first problem that I'm going to say. Let's say that we have 4 lines. I could make more lines. I have 10 lines in my booklet, but 4 is easier to draw here. And there is a line at the bottom. So I guess that these are the lines. I guess I'm gonna call this one Q0, and then I'm gonna call this one Q1, and then I'm gonna call this one Q2, and then I'm gonna call this one Q3, and then this is the extra Q. And so let me just call this one Q4, basically knowing very well that if my lines are 4, then they will be numbered from 0 to 3. Then the last line, which is an extra line, it's going to be 4, which is the number, but it's the 5th in fact. And so this is the problem. I'm going to invent some sort of pattern. So I guess this is a good pattern. I mean, why not? I'm going to have control NOT gates, and they will be connected from some wire to the bottom wire. Okay, so in this case, I have 3 connections, and clearly I could have as few as 0, and I could have as many as 4 here, and I have 3. And with the red, I'm going to say, really, what's inside the red is unknown to you. You know what kind of connections you have. The connections are at most 4, at least, I mean, 0. The least number is 0. And you cannot see inside. You cannot see inside. You can see inside now because we want to talk about it, but it's basically, you cannot. So now that you know what's inside, pretend that what you really see is this. And they are telling you, do something to find out what the pattern is inside. So fortunately, I can reestablish it because we want to talk about it. And so I tried to tell Elman yesterday what the solution is, and he said, no, let me think about it, because if I solve it, I'm going to be very happy. So did you get to that point, Elman, or not yet? Anyone, if anybody were to be willing to give me ideas or comments or questions online, you know, we'll take those, but I'm not going to wait too much. But that's always a possibility, right?
So remember what you said.
And now the question is, how can I find a pattern? And the procedure could be something like this. Put a white ball here, right? Well, which is, we can easily put a white over there because that's a 0. And if we don't put anything, that's a 0. And so all the circuits that have nothing specifically in the input, that means that they are getting a zero. I mean, just for the sake of a reminder, this is what we are dealing with, okay? And then if you say, well, more, give me more, okay, then how about this one? The vector that has a zero, meaning is zero, therefore the one is on the zero position of the vector. Okay, so that's what goes into the input. And now I'm going to talk to Elma, who may or may not have, Elma has power. So he may have not been able to think about it. It's just sort of, I have power. And spend the time thinking about how great that is. I don't have power.
I mean, yes, they gave me hint and said we can use an Hadamard gate.
Correct.
And we just get 50 and 50%, and I don't see how this will now tell us.
First, we want to use a classical situation. So look, all these gates that I have over here are classical. A control knot says you put white, nothing happens. You put white, black, where white goes on the control, nothing happens. You put black, white, it becomes black, because your black is on the control, and that changes the white on the target. Put black, you're going to get black, white, because black is on the control. And now, because you put a 1 on the control, the X that is controlled actually acts as an X. So it negates everything. So here's how I would do it. And I'm telling you, this is a baseline. And I'm also telling you, you can't do better than this, but you have to agree or think about it. Let's start with Q0, and I'm going to put a black on it. Yeah, I don't know what's going on inside, right? So I see it, but I don't really. So the control comes exactly as I put it in, that's not a problem. But as you can tell, right here, there is a control with this guy, which means that the white that I put here is coming as black. Which means the conclusion after this test is that there is Q0 is connected. Do you agree with me? That's a simple test by which you are going to find out that Q0 has a connection to the bottom because it changes the bottom. Any questions, any complaints, or any thoughts about this?
So you can everywhere check with black.
So I check everywhere, exactly. Actually, you know what? I'm gonna go like this. Q0 is connected, and now I'm gonna say we test Q0 and we know that Q0 is good. Like I'm gonna do it like this. Now I'm gonna I take the second wire, Q1, I'm gonna feed a 1 on that line. And then I'm gonna still feed a 0 on the bottom. And then if this goes through, you know, if it had a little anything over here, but there isn't any, then out it will come as black because we're talking 0 and 1, and this is a control bit. And this guy will have to be changed, but it's not changed, which means there is no connection. And because there's no connection, I know that this one isn't, Q1 is not connected. So I put the 1, which will say, if I am connected to the bottom wire, I will actually negate it. Nothing happens, so I'm not connected. So I'm going to go back here to say this guy is not. Then I'm going to go here, and I'm going to put a third one, I'm going to put a black qubit. And then because of this guy over here, the qubit is going to come out, not because of that, but it will come out because it's a control qubit that's completely unchanged. But because of the arrow that you saw over here, the white is going to be transformed into black. So you remember that the control knot says if you put a white on the control, the target is unchanged. The control is also unchanged with 0 and 1. And then if you put a black on the control, then the target gets flipped because then the X actually finally works. So I'm going to go back here and say, that's what I told you about that one. And we can say that the experiment indicated that that one is connected as well. So then I have one more, and I put a black over here. And it comes up as black. Now what happens here? The outcome is white if there is no connection. We know there is a connection. So even if you don't see that it's a connection, we know that the experiment is going to produce a black over here. Well, if it does, then not knowing what's inside, we're gonna conclude there must be a connection over here. So test the wires one by one, and the conclusion is that's the secret number. How many attempts did I have to take? 4. I say check 1, yes, check 2, no, check 3, yes, check 4, yes. And if I have 10, so this is how many wires do I have? This is the number of wires. It's going to be n equals this n. You like my n, you don't? I'm gonna say this is n equals 4. In my thing is 10, and it doesn't matter if it's 100, it's 100. You go step by step, step by step, step by step. So that's the problem that we have to solve. Can we do better than n tries? And specifically, we have been told if you use quantum gates, we are not using any quantum gates. I mean, yes, control not is a quantum gate, but here with zeros and ones, it acts like a classical gate. The only gate that we know that's quantum is the one that produces superposition. Use it with 0 and 1, and you get a strange state which you cannot produce with classical gates. That's a Hadamard. We have to use Hadamard, right? But how? Exactly. Okay, so Hadamard is going to come to the rescue. I'm going to use the eraser now to say, let me give you a different problem to give you a clue as to what we are supposed to do. I'm going to invert this problem, right? I'm talking about different problem now. Different problem. Here's a different problem. Let's say that I'm going to have the same number of wires, and I'm drawing them over here. But the situation is exactly opposite. The control is on the bottom, and the target is on the wires. So now the question goes to Elmar. Do you think that with the same tools that we use so far, you could actually do better now? Or you could say, I don't know. You could say, yes, I know. Here's what I think. And as I said, if you say something that's wrong, it's not your problem. It's everybody else's problem. And if you say something that's good, then it's to your credit. Hats off to you and so on. So in this problem, can we do better here? I'm gonna use black and say, can we do better here? I mean, compared to this. Oh, look at that. So I'm gonna erase this. Can we do better? That's the thing. So anybody online or Elmar or me, how do you think we can do here? Elmar, any idea? Just a quick thought. Anybody online?
I don't have any.
We don't have any idea here. Anybody online? If you don't have any idea, no problem.
I mean, I know I have to put the Hadamard gate in each.
Forget the
wire, but-
Hadamard gate. Here, you can do it in one step. So here,
But it doesn't, I don't see.
one step without Hadamard. So I want to emphasize that I told you, and I will repeat, that quantum computing can produce breakthroughs in some areas. It's not that quantum computers are going to run out completely and eliminate classical computers. This is an example. This is a situation where you don't need anything quantum. This one, the second one, this one here. You know, you don't need anything. You can do it in one step. Okay. The problem is that you cannot do this one classically. So I have to choose carefully the problems that have a limitation for the classical field. And then I come and say, so that problem is solved by quantum. Then I say, this is the advantage of quantum in this area. I cannot say that quantum is going to have an advantage everywhere. I'm choosing my problems very carefully here. All I'm saying is there are problems that classical computing cannot solve faster than a certain bound. I mean, margin, whatever, and then I come with the quantum gate and I solve.
They're black and then you get the number out.
So the idea here on the right is this. I'm going to put a black here. Is that what you said? Yeah.
Yes, and then it should. No.
Then depending on what I have on the
But
others.
this is the output layer.
yeah, I'm gonna do this, then boom, I have a problem in which I can easily create things in parallel. So every single gate in this problem, which is not, so this problem is problem number 2, is not my problem. This one is my problem, but I can change the problem to just get an idea. So this is the problem that we are working on, but this is an example that can produce ideas. So you see, if you put it on Q4 on the right, a 1, then if you put whites everywhere, then those whites that have a target will be changed, because that's how this works with 0 and 1. So if you get this here, and then you get this one here, and then you get the same white here, and then you get this one, in one step, I got the answer. But I cannot use the same method here on the left, you know, can't use the same here. Because the things are backwards. And if the target is the one that is going to report whatever the control did, the wire at the bottom on the left is acting like an OR. And so if somebody turns that wire on, then I don't know which one did that. And so I have to go step by step. That's my main problem. Okay, but the idea on the right, idea is great. Okay, I don't know how to say great here, but something like this. Okay. So if people understand the thing on the left, I'm sorry, right. This, if you understand how we came up with the situation, or this actually is good for us, then all we have to do is to convert the problem on the left to this, if it's possible. And have you seen this? Have you seen anything like this yesterday? Meaning, is there anything that switches the role of control and target? Yes.
I have a question. That you said that on the left side, it's like a OR.
Over here is like an OR. This
Could
guy,
you
this guy is like an OR.
elaborate on that, because I don't see it.
Oh, sure. The OR on the wire at the bottom is saying that if I get a black over here, it's because there was somebody acting here, or here, or here, but I don't know which one. There may be all of them.
That's why we have to do it one of one.
Exactly, one at a time. But here I don't have to do it one at a time. Because essentially it's backwards. And so I'm coming and say, if you have a target on that line, you will be turned on, flipped. And nobody interferes with what you're doing. And if you flip, then you have a connection. So are you connected to the bottom wire on the right? Yes. And the parallelism is acceptable here simply because the one control can control many targets. But here you have many targets being controlled by various controls, and then either one of those controls sending a bit of one will turn the wire at the bottom on one, and you don't know. It could be one of them, 2, 3, all of them. So
I see.
So the idea now is, I like this thing, the one, I said the idea is great. So let's use this idea on the left. So what I'm trying to tell you is that the idea is, I would like to flip my gate. Well, I'm flipping it here. I am able to make the control act as a target and the target as a control if I use phase kickback. So in comes a minus.
C0, right?
Yeah, it's the same C0. Okay, but it's flipped. So now I'm going to say, as long as you understand what I did on the right, which represents basically the main idea. As long as you understand, I'm going to erase it. And now I'm going to change the thing on the left so that it acts like we decided. Okay. I'm going to say, is my eraser, come on, eraser, move. You know what? When you are going to finally move, I will be happy with right now is I'm happy. So I'm gonna come back to this and I'm going to say, what was the basic example? Example is I have 4 wires. And then there's a wire at the bottom. And the pattern was something like this. I'm going to connect the last wire, the one above it. That was the pattern that we had at the time, and then the top one. And then there's nothing on the wire that's number 2, and that's okay. So which part do I not know at all? This part. And what am I supposed to do here? Classically, all I have to do is to feed zeros and ones in such a way that individually I talk to the
Plus or minus.
but if I put plus and minus, that changes completely. And I suddenly have good things. So I'm gonna put plus over here. And I'm gonna put plus over here. And I'm gonna put plus over here. And I'm gonna put plus over here. But at the bottom, I'm gonna put a minus. And so what happens? Now I flipped the gates. The targets act as a control, and the control acts as a target. So what comes here? The minus says, you know, this base kickback, so minus is going to run everything. So you get the minus completely unchanged. But you also get this plus changed, and you get this plus changed, and you get the plus here unchanged, and you get a minus over here. So essentially, I just flipped them the way I did the other one. And you're gonna say to me, but we do not have pluses and minuses. We have zeros and ones. So what do I do? Then you say, wait a minute, how do you get a plus? And you get a plus, right? This one, for example. So you put pluses everywhere except in one place. You get a plus by feeding a 0 into a Hadamard gate. Okay, and now you have a 0 over here. Well, of course, the 0 is the same thing as the white wall. Great, now if you don't put anything, you get a white wall. So put a Hadamard gate here as well. And you know you're gonna get a plus here, and you're gonna get a plus over here, because we already discussed that H of white is gonna be a plus, and the plus is what you just saw over here, because we discussed this before. So I'm going to put, yesterday I said, use Hadamard gates. Why? Because of, I want to flip everything. And finally, I do put a Hadamard over here, because I need to get a minus. But when I get the minus, I have to have a 1. So by default, I don't get that 1. So I have to put an X in front of it, so that when I put the white, then that becomes a black, which then produces the minus. So I'm going to go and say that now this is how I create all the pluses. And then the result is that all the pluses will be turned into minuses because of phase kickback that we spent time yesterday and the day before solving. And all the wires that do not have a connection will just keep the plus altogether. So I'm going to use the eraser again to say, you know what's coming on the other side, but people have asked you specifically to produce the number as zeros and ones. So all you have to do right now is to say, I'm going to put a Hadamard gate here, so that although I'm getting a minus, out of this I get a 1, which is a black ball. Then I put a Hadamard gate over here to get whatever I get, and I put a Hadamard gate over here, so that every minus or plus that comes out is going to be converted, and I don't need anything over here, just leave it the way it is. So this one here is the plus that has no connection, and it's going to come out as a plus, which will then produce a white. This one here is going to be a plus that has a connection that's going to go through. You guys can see my little dot. I have a doctor appointment, so I'm very sorry, no problem. They also called me to schedule something next year in June. So in the middle of the lecture, so I hope everything will be good. Go ahead and take advantage of your doctor's appointment. Now I'm going to, and maybe she just wrote to me and I wasn't supposed to share with everybody, but thank you so much. So I'm gonna go and say, for example, this guy, this one here, because you see the little dot on the screen, the plus comes in and says, I will become a minus. And here's the minus that comes out. And out of the Hadamard, I'm gonna get a black. And then I'm gonna get a black here as well, because the plus has a connection over here. And that's going to turn into a minus, and the minus goes in this. So you already saw the idea. The idea is available. for a flip configuration in a classical sense. And with that, you can then say, I have the idea, and I also have the tool, that's the phase kickback. So if you gave me that problem, I could in fact benefit from the phase kickback because I can apply the idea that I have in the other problem, such that the wire at the bottom controls all the other wires. And that's exactly what's happening in phase kickback. And I put pluses everywhere and minus on the bottom, and then I just read the secret number on the outputs. So how many attempts? One. I feed everything, I get the output. End of story. That's one try. Before that, I had to do one wire at a time. And this is a quantum gate that makes this solution quantum. Without it, I mean, I don't have anything. So that's a quantum gate because it produces a position, which is totally not classical. And now I'm going to say that I'm going to come back here and the chat.
But you need,
Yeah, it was a direct
10
message. I'm sorry,
gates.
Carla. What?
you need 10 more gates, right? You have all, I mean,
I need Hadamard gates to get the pluses.
yeah,
Yeah.
yeah. So, I mean, of course, you get it in one step, but you need much more hardware.
So what? The idea is that I can get it in one step.
Yeah, okay.
Okay.
Yeah, I mean,
You know, you say, but you need much more hardware. I'll give you as much classical hardware as you want. Go ahead and do it classically in one step. And you say, well, I can't.
again,
Exactly.
yeah.
So yeah, you need a little bit more.
It just
No problem.
point it out.
Correct. You need the Hadamard gates
Yeah.
on every wire. I'm going to say replace current share. I'm going to come back here. And here we are back into the regular thing. So what I would like to do is to say, okay, whatever that means. I hope that at this point you understand the problem and the solution and the benefit of having worked out the phase kickback. So it's 9:30. Hang on, let me just go back to this guy. I said I'm going to write code and I'm going to show you the implementation of Birthday Vazirani, because you need to be sure that it works. And if I give you the old video from Abe or whatever I wrote in the booklet in Kubica, it doesn't work like that anymore because they keep changing things every so often. So I'm going to go back to Zoom here, and I'm going to change the problem completely. So here's me in a form. Am I sharing the screen? I'm not sharing the screen. Okay, come on. Zoom. Please come back to me and let's share the content. I would like to share the screen. Now I'm going to start broadcasting. So with this shakeup, I already finished the problem, and you know I'm going to go and write the code, which I did yesterday. I'm just going to show you that works for you, and you should reproduce it and then try a few variations and so on. But with this shakeup, I'm going to come back here. I'm going to say, let's erase everything, and let's introduce the idea of entanglement. And tomorrow, what I promise to do is so I introduce the idea of entanglement and explain to you how you produce it and why it is what it is, and then you write the code for Birthday Vazirani, and then tomorrow I'm going to show you that if I take the circuit that I will demonstrate or show you or explain to you today, and then I actually go in and measure it, then I will automatically get a distribution of outcomes that will basically explain to you what entanglement is. Although today, in the case of Birthday Vazirani, there is no distribution because in one try I get the number. If I want to do it repeatedly, I repeatedly get that number because I'm that good in this particular algorithm. So I'm going to say to you the following, that suppose somebody gives you the following circuit. Here's a Hadamard gate that takes you into the control of a control knot. And I'm asking you to please tell me what's the output of this state. Okay, so you're going to tell me, oh, you don't put anything in the input. That means there should be a white here. Yeah, I am looking at the other screen. Okay, and then there is a white over here. So what's happening now? Basically, I'm going to say that I will take the eraser and now put this thing a little bit more separated, so that I have room to write in between. So here's the control here. And here's the gate that will be controlled by whatever I'm putting on the thing. And this is a wide circuit because I want to say, what do you think I have here? And the answer is that. Right, but every time somebody gives me something like this, for example, if you say, but what do you talk to people who don't know the mixed state formalism? Let's say this helps you, but they don't want to learn it. Then I'm going to say there will be a 0 and there will be a 1. And is that a plus or a minus? There's a plus. And what do you put here? And what do you put here in front? And clearly you are going to say it's going to be 1 over square root of 2. And you can calculate this with what's in the book, with what we described in there. I mean, you in the booklet as well. Good. So you know how to convert these states, but now we're going to do mixed state formalism. Okay, then my quick question is, what's going to happen here on this wire? On this wire, the white stays white. So people can say, could you combine these two into a combined state of 2 qubits? And the answer is yes. It's going to be this as a qubit, but it's a superposition, followed by a white qubit, because that's what the second qubit is. And then this is the reverse of what we did yesterday with Elmar. And it's going to be something like the superposition now surrounds everything, and we have either white-white or we have black-white. And that's the meaning of this. I either have a superposition of white and black, followed by a white, or I basically have 2 outcomes, you know, white-white, black-white, where clearly the second one is always white, but the first one could be either white or black. So you could combine this, or you can keep it separate. I'm going to work with this combined state. I'm going to say, let's take the control knot and apply it to this state. So I'm going to say my control knot is a knot, first of all. And then which one is the control bit? It's on the left. So I'm going to put the arrow this way. And what's the thing being applied to? And I'm going to take the superposition that I just calculated, which is white-white, followed by black-white. And so I'm going to say that when I apply a control knot to a superposition of states that each has 2 qubits, because it's supposed to be consistent, then I put the superposition operator on the outside, and I'm going to apply the control knot to white-white, and I'm going to apply the control knot to black-white. Now you see what's happening. The state that I used to have, which was expressible in 2 different ways, I could just have a superposition of states of 2 qubits, so I could have a product of a superposition and one specific qubit, is going to become impossible to describe as a product. And that's the definition of an entangled state. So I'm telling you this for the first time, and maybe you don't understand what I'm saying. So we are going to say it again and again, but I said something that it makes sense, and you may already understand, or maybe not, then I'm going to have to explain it again. So what happens over here is I'm going to get this, and then here I have this. Okay, clearly because the second one is going to change because the target, it is a target of the black qubit. See, and this is impossible to give a factor of any kind. This is an entangled state, a Bell state, because it says the following. The outcome is going to be either, when you measure, white-white or black-black. Okay, what's even more interesting, and we have to go over that derivation separately. It's in one of the Vazirani videos that are in the playlist that are listed. If you just measure one of them, automatically you determine that if you measure the first qubit and it's white, then clearly you can't possibly get a black on the second one because that's not listed here. That's not a possibility. And if you measure, let's say, the other one, and you get, I don't want eraser, I want this, and you get black, for example, just as an example, then clearly you're gonna get black on the first one because that's what you have in the list of outcomes. Right? So you measure the second one, let's say, and you get a white. And the first one must be white. Whatever you do to it, even if you don't measure, it is white now. Because the outcomes restrict the possibility of getting a black-white or black or white-black. Because that's what you have over here. They are entangled, and this is the phenomenon that we described, I guess, or you encounter that if you measure one, the other one is already set by the measurement, not on it, but the measurement on the other one. They are connected somehow, like they are telepathic in some quantum sense. And therefore, even though you don't measure them, because they are entangled, measurement on one forces the other one to choose a state, to collapse. All right, that's the example. And so over here, I'm going to say that if people ask you what you have over here, you're going to say it's the following outcome, either white, white, or black, black. Okay, you're done. You cannot explain this as a product of two states. This is no way. It's 0, 0. And all you can do is you can say over here, this is going to be 1 over square root of 2, 0, 0, plus 1 over square root of 2, 1, 1, if you want to describe this in the conventional sense. So why am I bringing this up? First of all, it is fundamental. Second, because the first time you see it, and we need to use it in super dense coding. We need to use it in CHSH game, which John talked about last week. We need to use it in the GAC game. Entanglement is fundamental in communication, but it's teleportation, for example, which is also communication. Let's see. So we have to learn it. Because it's going to be used. GAC does the same thing. Without it, we wouldn't be able to break, Bell's inequalities and so on. And now that you understand it, you will be able to maybe experimentally explore it. So as I said, if I create an entangled state and then I want to measure it, what tells me that I'm going to get 0, 0? Nothing. What tells me I'm going to get 1, 1? Nothing. So I'm going to get roughly half the time 0, 0, roughly half the time 1, 1, but I'm not getting anything else. And that's what you should see from a simulation on a Bell state, that you're going to get a distribution that's roughly half and half. If you're doing it on a regular hardware, quantum hardware, then it's going to have some noise. It's not going to be exactly 50%. But if you do it in the ideal setting, then depending on how it runs, it's either going to be close or it's going to be ideal 50-50. And so that's an entangled state of two qubits. And as I said, it has meaningful implications. Of all the things that we're going to do this semester, there's one called entanglement swapping that I will mention and explain, but not do anything about it. That allows particles that have never interacted directly to become entangled. So that's an interesting phenomena, and this is the extent to which we bring quantum mechanics in our discussion, because all the things that we do are supposed to have a very clear computational aspect. So I'm finished with this, and I'm going to go to this other one, and I'm going to go and run the experiment. 9:41, I have 20 minutes to do the experiment for so when I come back to Zoom, where is my Zoom? Right here, and I stop sharing. Then I come back here and I say I would like to share. I come back in this place, and that's great. Let's see what I want to do. I don't think I'm going to use the iPad anymore, so I got other things to charge. So I'm going to quickly disconnect this. I'm going to say okay. Just a second, I'll be on Zoom in a second. Yeah, well, I guess that's not. Meanwhile, this guy was being charged, so I don't run out of power on it. And as I sort of explain and I draw. So now I'm putting this. I'm just gonna put a bunch in there. And now I'm gonna come back over here and I'm gonna say, I do all the calculations in Google Colab. But by the way, I will find the thing from yesterday, but I'm gonna ignore it. Or if you want, I'm gonna just delete it. So I'm gonna say new notebook. I ignore the thing that I did yesterday, and I'm gonna see if what I have right now, Control-Alt-Shift-H, online. What? Control-Alt-Shift-H. Okay, good. So I come back over here and I say, if you look at students, go away. Okay. Go into group, and you can do the same thing. Your goal is to make sure that things work, and then you can say, okay, I'm going to challenge myself to do it without any help, or I'm going to modify things. So what happens here is I'm going to just move things from this notebook into the other one for you to see that if I do what I say, it does exactly what I posted, so I'm not inventing anything or making things up. So the first thing that I do is a code cell, and it will install Qiskit as well as the part that deals with, let me show you the LaTeX version of the quantum state. All right, this takes a while. As I said, this is a free thing. Therefore, anytime you install, you need it. I'm sorry, you have to install it. It doesn't stay between sessions, and in fact becomes inactive if you wait long enough. So when this is finished, it's going to indicate so, and I'll take out the output. I now have Qiskit, and I have the part that deals with show me the output. For the first time, though, we are going to measure things.
So
Yes.
I have the question to entanglement.
All right.
So if you have on your second line, not another line, a black ball, then you get always the opposite. Is this entangled too?
Yes, it is. So I think that what the question is from Elma
So now you
says,
have white, black,
Okay.
black, but then you have
yeah, absolutely. He's asking, you gave us an example for white, black, black. Can you do white, black, white? Yeah. And yes, there are 4 pair states, with plus and minus, and then white, white, black, whatever.
Okay.
But I do have the one you're asking very early into the booklet. So if you go through, this is like forward again. And as you go through this, and I'm introducing various things, I say, hey, by the way, let me show you some Qiskit. This is a formula for the probabilities, as I was telling you. And then if I scroll through this, this is a circuit that produces 0, 1, 1, 0. And that's exactly what you were telling me. So here's the H that feeds a superposition on the control, and then you have a knot here. If you, instead of a white, you put a black, then you get what you just described.
yeah.
There's no minus here, but there is a way to get the minus too. So you get 0, 0 plus 1, 1, 0, 0 minus 1, 1, 0, 1 plus 1, 0, and then 0, 1 minus 1, 0. And then you have 4. So that's good practice. Okay, and they're all entangled. So this one says that if I measure the first qubit and it's a 0, the other one immediately is set 1. You have no option because there's no other possibility wherein the outcomes, the first bit is 0.
I mean, I see now how you can entangle two parts. One.
I entangle them in such a way that when one is measured, the other one also has a definite state. Now, which state is that 0 or 1? That's why there are 4, because you have different combinations.
So do you can produce them, but do you know? You never know if something is entangled or not. If you collapse,
If I produce this, I know they're entangled.
when you produce them, yeah. But I think it really nature so happen that things is entangled that you don't know.
Oh, wait, I'm not a physicist exploring nature, and somebody gave me 2 qubits and say, tell me if they're entangled or not. That's not the problem yet. The problem is, can I produce 2 qubits which are entangled so I can use them in meaningful
Yeah,
computational
okay, yeah.
ways? Is that like, well, I'm Lieutenant Colombo, I'll tell you if they are or not entangled. Or some other guy, House MD, well, are they entangled? Let me just run some tests first or something. That's not the case here, right?
Yeah, okay. So,
I want to produce entangled states for a very specific engineering goal.
yeah,
But your problem, the thing that you are asking, that may be very interesting and maybe difficult. Who gave you those qubits, right? Why are you investigating them? Well, they're coming from the outer space. Oh, okay, that's nice. Well, how can I tell that they are entangled? You know what? I'm just gonna say you can't, because you don't know what state they are in. And when you measure, you get something, and it's very difficult to say they were entangled because look what's happened. But the definition of entanglement is that anytime you measure and you get, in this case, for the one I'm showing you with the mouse, that gets 0, I absolutely know that every single time the other one will be 1. So I'd have to repeat it, but then I consume them after the first measurement.
yeah.
If you have a source of identical qubits, for example, photons, right? And then you say they all come in the same state. Again, I don't know where they're coming from, but they're coming like this. Then I can sort of keep measuring and say, what I determine is that these qubits coming to me, they're all in the same state, right? One after another, one after another. They come in entangled state. If they are, who tells you that they are in the same state? You have to assume, or you have to be told by somebody. We are
Yeah.
producing them in, but can you determine if they're in entangled state? So this is a physics problem, and we're not going to be able to solve it in this class. But you can talk to Gerardo or anybody in a minute. Let me tell you. what else do you want to do, or why are you doing this? Our goal here is to produce qubits in a certain state that will then help us in communication, sensing, or in calculation. So I'm gonna say that once, yeah, you're welcome. But this is a very good question, and unfortunately, as soon as it gets into physics, I can't really provide a purpose anymore.
Yeah.
And also sometimes the actual solution I can. So then if you go into the solution, I mean the chapter for Bernstein-Vazirani over here, and you look at the thing, this is the state that we talked about right now. But look, this is another state. So you should just practice this and see what happens with the three qubits. The outcome is that they will be GHZ, three European scientists. They came up with a state which is either white, 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 or black, black, black. And at some point, this is sort of shown. Here's another Bell state. You see, now I put a Z in there. This is 0110 with a minus on the first one. That's really how you produce a GAC. Again, this is being traced. And this is a slight modification on the circuit where you also get a GAC state. I mean, see the white, 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 or black, black, black in superposition, but the gates seem to be like different connection. And that's the phase kickback done in a certain way, and we did something new yesterday, and this is the Bernstein-Vazirani, and if you go through the code over here, unfortunately, this code is not going to work exactly as here because they changed it, and now I'm going to show you how it should work.
Yes.
So I installed this guy and I took out, okay, the output because I don't need it anymore. Then I'm going to import Qiskit. And that's good that I import Qiskit because I need it. So do I have Qiskit? Yes, I could have tried that before and they would have said, you don't have Qiskit. Now we install, then we have it. From Qiskit, I want to import everything. I'm not sure exactly right now what I need, but it will become clear in a second. So after I install those two packages, modules, and then I import one of them, and then I import everything from that package. So I don't have to say Qiskit period, and so on. Now I'm going to go and say, here's a secret number, and I want you to know how you're going to control this. The secret number is going to be a sequence of ones and zeros, and then they have to come in pair with a list of indices. So 0 reflects on this one here, and then 2 says there is a 1 here, and then 3 is 1 here. So one thing you can do is you can determine the indices by looking at the string, which I didn't do. I said, here's the indices, here's the string, now I can do the work. So you can make the program smarter if you want, if the program is actually pulling the indices out of the string, because that's what it's supposed to mean. So if you have this one, then I'm going to go one by one. Yesterday, this didn't quite work for whatever reason, and we had to restart it, I guess. So now, hopefully it's going to work. And what I have is, give me a circuit that has n+1 inputs, right? And then will allow me to make measurements on the first n. So this is a circuit that has 1x, and I'm going to say circuit draw, and the output is going to be, what yesterday wasn't kind of coming out, is equal to MPL, like so. Do you see my circuit? It's a 4 inputs with a 5th line that has an X. So you say, okay, I understand this. This is responsible for that. If I want to simplify this, and I'm going to say, let me just do 1, 0, then I guess it's going to be a 0 over here. And then the n is still the number, but the circuit is going to be much smaller, see? So I do say that this is very flexible, but it could be made even more flexible. So if I'm going to come back over here and do what I had before, I have a 4 input circuit with the indices indicating where the ones are, so I don't have to look for them myself. I create a barrier, and then I put H on basically all the inputs, including the last one. So then if you're saying, good, your circuit now gets bigger, and let's not put an H at the bottom yet. When I run this, that's the circuit that I have. The H applied to range of n means I'm going to put H on 0, 1, 2, 3, and that's it. That's the range of n. And if I say I want one on the nth one, which is like the fifth one, if I have 4, then the circuit now has an H at the bottom as well. So this gives you an idea as to how things get together, be put together step by step. The barrier is when a gate is missing here, I can still align what's coming after because of the barrier. If I take the barrier out, this becomes a little bit of a mess. So I think it's a pretty good tool. I will take the barrier out, see, and then if I draw this, all the H's go to the left flush, and then the H after the X is out of place in some sense, just aesthetically saying. So the barrier is going to help you organize things a little bit. Now that I put it back, then the barrier is going to be there and say you have X with nothing else, and then all the H's are aligned, and that looks more logical. I'm going to use the index variable going through indices like 0, 2, and 3. So I don't know, the list allows me this. The set may or may not, set shouldn't have an iterator. The set shouldn't have an iterator, right? It does, of course. But that's why I'm going with a list, because I like to go through those indices. And the set is also, of course, does have an iterator. Because you can say, give me all the elements in the set one by one, and that should be able to generate those. Wait, he likes sets very much, and I totally agree with him. Except I keep using the list, and I don't want him to think that I have something with the sets. I don't. And look at this. I forgot the barrier, but now I have my nodes, the control nodes. There's one from Q3, there's one from Q1, and there's one from Q0. I hope you understand that this diagram is going to give me the reversed answer because of Kiski, which always reports from 3, 2, 1, 0. Whereas if we were to write a state, but we don't do this here. We just look at how things appear and then we say, that's it, it's the same. But if you want to produce a string that is the same that you would produce from Misty State with Qiskit, then you have to flip things at the end. That's the reason for which in my booklet you will see a diagram for the see, this is the diagram that you have in the circuit, but this is the reverse diagram in the picture. It's exactly opposite. See, so the fourth one is the last wire with the bottom one. And here is not the last one, it's the first one, because I want it to be the same string, not the reverse string. So I'm going to come back over here and I say there must be a barrier over here, and then you put all the H's. I guess I forgot this barrier. I'm going to put everything down in. So as I come back here, I'm going to say after all the H's, this is what I have. There's a barrier after all the H's, and there's a loop, then another barrier, then a bunch of H's, but I don't have an H at the bottom. And so here's the circuit, and this is how I draw it. So the very quick question that I have here is, what do you think will happen when I say, would you please give me the formula of the state? What state am I going to get? So if I have 0, 0, 0, 0, and there's a 0, it becomes a 1. The 1 is supposed here, I have to have an H for the minus, which I think I lost it because I didn't do this. And the minus will act as a control on the targets. And now I put it over there in the wrong place, man, unbelievable. This is at the end, because I want to decode that. But the one I wanted to do is here. So circuit H on N. Okay, and so when I do this, then that's the H over here. So white becomes black, put inside H becomes a minus. The minus is going to control the targets as if they are controls, and all the controls become targets, and all the white turned into plus will now be changing if there is a connection, right? And I'm going to get the output over here. So there's a white over here which produces a plus. The plus changes to minus. Minus is going to produce a 1 over here. I got two things that I want to show you. First of all, that's the circuit. And do I want to recover something here or not? So I'm going to first tell you that all the things that we did so far essentially were to produce a state. Okay, so here's the state, and how do you guys feel about the state? I'm going to say, yes, you should feel good because it's 1011 here and 1011 here. So whether the first qubit in this expression becomes 0 or 1, the rest of it is the string that we were looking for. 1011. And if you say, well, I don't believe you, okay, then how about I take this another string, it's much longer, and the indices associated, these are from the book, right? And when I run this guy and I draw the circuit, it's a much bigger circuit. And when I run this guy, look at this, the same situation happens. This is the string that I was looking for. 111001, 0001. And that's 111001, 0001. And then the qubit in the front is either 1 or 0. I don't care about that. And if you say, but apparently you could have also put an H over there. And so you're exploring, first of all, with what we knew so far, you still are able to produce the answer. And all you have to do is know how to read it. Now you're reading everything as zeros and ones. There is no superposition. Without the H at the bottom at the end, you would have to do the 1 over square root 2 minus 1 over square. But now you have the same thing, and please don't consider this one because you know it's the one. And the rest is 111, 001, 0001. That's the string we were looking for. And suddenly it's a different string, right? As long as in my code, the indices and the string are 1, then you see this running. So the last part in this code is, let me run it with some sort of simulation that indicates if I run this a couple of times, then can I plot the histograms as to what I got. So for this, you have to install a backend, which does the simulation, but this is not producing the phase function, the wave function. This is going to simulate it, like I said, with the probabilities and give you some statistics. So after I install this one, and that's the thing that changed, you have to set it up so that it measures the results. And I'm going to put this here, show you that this is working. And you might say, well, where did you get this? Because the book apparently that you wrote is outdated. I agree with you. This is where I got it from that link. Maybe I should have put something in here and I didn't. There's a different link that this is the link, this is the tutorial. So I'm gonna, did I do that or not? Yeah, I did. So next step would be this one here. So I'm going to create a result, which is made of, just give me one shot. Okay, do not measure more than once, because I claim that in one step, it's gonna be fine. So I got the results, now I have to plot them. When I plot them, I say, you received what you received in one shot. And what I expect here is the longer circuit, because I changed the circuit. So 111, 001, 0001, because we changed that thing. And if you wanted to plot, then this is it, and we're done. So plotting is going to say, what did you do? You wanted a circuit. There you go. The secret number. There you go. And how many shots did you do? So if I take the number of shots here and I say, don't make one, just run it. It automatically will run for 1,000 times, 1,024. And when I print, it says, we did this, and every single time it came back. Then you say, okay, here's a histogram that says that for 1,024 times you get this number. So here the simulation makes no sense because we claim that we can do it in one try, and then if we do it 1,000 times, in that 1,000 times, every time we get the same thing. But at least I showed you that this is working. And so we built a circuit that represents Bernstein-Vazirani. It works the way we explained it. There's phase feedback inside that does the work for us. And then we did two things. We printed the phase, like here. That was a simpler way. I don't want the code, but anyway, I clicked by randomly. We print the phase again. If be careful, because if you put a pound sign over here, then the phase looks slightly different. We discussed that, and both should be easy for you. But the most important thing today, I'm going to get rid of this output. The most important thing today is that you can run the circuit a bunch of times and then get the histogram. So we'll do the same thing with entangled states tomorrow. And you will see that we will get half the time 00, half the time 11. Because that's the probability for that superposition state, but we will never get 0, 1 or 1, 0. Because the entanglement state says when one is 0, that one. If one is 0, the other one is 0. And if one is 1, the other one is 1. That's what that state says about entanglement. That concludes our lecture today, and I look forward to tomorrow. And so far, we don't have meetings this week because me having issues, but if my call comes back, I will let you know, and I'll invite you for meetings if that's possible. But looks very seems very skeptical that they will fix this. Okay, if anybody has any questions, I'll be more than happy to take them now. If not, let's see what happens. I'm gonna do escape. We have 6 people still in. Thank you very much for your patience. I'm going to stop recording and then discontinue now. I'll post this recording maybe in an hour. Very good, thank you. Tomorrow I'll also go through the diagnostic quiz. We have all the questions and the answers, and I'll show you at 15 minutes how we put everything together in a notebook. And if people have questions about those, we can look into Bird, which has math for matrices with NumPy in Python, or we could just discuss or go into Wolfram Alpha and so on. And that would completely finish week number 2. Next week, I'm thinking we should look into Deutsch Georgia and Grover. However, I did write a template, a schedule. So we should check what I wrote at the beginning and try to match whatever I wrote before the class started. But that's, I think, what's coming. No entanglement in Deutsch Georgia and Grover, but more quantum advantage. Thank you once again. I'm going to close the participants. I'm going to close the chat. Yeah, thank you very much. And I will be in touch. I'm going to stop sharing and I'm going to turn the video on so you guys can see us as we are going to click stop recording.